Hello. In this video, we're going to be talking about asymptotic complexity, otherwise known as algorithmic complexity. We'll discover what it is to time an algorithm, and also why input size n needs to be sufficiently large. We'll introduce a notation called big O notation, and also introduce the complexity classes, or sometimes called order classes. Finally, we'll look at some examples. So let's get started. Algorithmic complexity is different from benchmarking. We are not interested in how long a particular dataset of a particular size running on a particular piece of hardware will take when running a specific algorithm. Calculating algorithmic complexity or analyzing an algorithm's asymptotic complexity is an analysis of the running time of an algorithm that usually involves an estimate of time as a function of its input size n. The asymptotic behavior of an algorithm or function refers to the growth of this function as n gets large. It's not until n gets large that the true nature in terms of performance of an algorithm or function becomes apparent. Let's envision a race with two runners, runner 1 and runner 2. What if the track is 3 feet long? The race begins, the runners run towards the finish line, and runner 2 wins. Does this really mean runner 2 is better or faster than runner 1? Could you even time this race accurately? What if the track is now 20 miles long? The race begins, the runners race towards the finish line, and runner 2 wins. This time the runner's true nature can be observed, their training, their endurance, their speed. If runner 2 wins this race, we can feel more confident about runner 2's performance and declare runner 2 the winner, saying runner 2 is better. Take this analogy and use it for algorithms. The longer track represents input size n being sufficiently large, enabling the true nature of the algorithms to show. The runners would represent the algorithms. On a small track, either runner could possibly win, but we couldn't truly say anything about which runner was superior to the other. Similarly, with a small n, it's possible an asymptotically inefficient algorithm could complete the task at hand before the more efficient algorithm, the algorithm that's asymptotically superior. Once again, with small n, we couldn't say which algorithm is better. The rule of thumb is, the slower the asymptotic growth rate, the better the algorithm. Big O notation describes the asymptotic behavior of algorithms on large problems. Big O notation is simply a label, such as big O of n squared, that represents the set of all algorithms that grow at the same rate as n squared, or a quadratic algorithm, or more slowly than that. In other words, it's an upper bound on how inefficient an algorithm can be, in other words, representing its worst-case scenario. Here are a list of some order classes. These classes are labeled using big O notation. All algorithms fall into one of these order classes. All algorithms within a single order class, let's say big O of n squared, grow at the same rate. They are not identical, but the nature of all of these algorithms in the same complexity class are the same. A quick note about log. Here, log is log base of 2. So big O of log of n is really big O of log base 2 of n, and so on. Let's take a look at some algorithmic examples. First, a note about constant time algorithms. If an algorithm executes the same way in the same time, all of the time, regardless of the size of the input, then this algorithm runs in constant time, or big O of 1. If an algorithm takes x milliseconds, and takes x milliseconds if there are 5 items in the input dataset, or 5 billion items in the input dataset, then we consider this algorithm a constant time algorithm. In other words, this algorithm time doesn't change when the size of the input changes. The 1 here is symbolic for constant time and doesn't literally mean 1 second or 1 millisecond. Examples of constant time can be assignment statements, push and pop stack operators, returning the first or the last item in a list, and so on. Here's an example. This function returns true if the first element is null, false otherwise. Does it matter if there are 10 elements, 10 billion elements? No. This algorithm will run in the exact same amount of time. Therefore, this is a constant time algorithm. Here's an example. For I in range n, total is equal to total plus the value in the ith position in a list, and then we print the total. So what's going on here is that we have a loop on an order of n, where n is the size of the input a. So we're doing this n times. Now, what if we change the size of a? Currently it's 5. Let's double it and make it 10. How does the time of this algorithm change? Well, it doubles. If it took X amount of time to process 5 data items, it'll take 2X amount of time to process double that, or 10 items. Therefore, there's a direct relationship between the size of the input and the time that it takes. And this relationship is linear. Therefore, it's big O of n. A visual is to look for a for loop. The for loop has to count, however. What does that mean? It has to be on an order of n. It has to pertain to the size of the input. Let's look at another example that has many for loops. Can we just count the number of for loops and say, oh, this must be big O of n to the 3, or cubic? I see 3 for loops. But that's not actually the case. First of all, the for loops need to be embedded within each other for it to count. In other words, if I have 5 embedded for loops, then I can conclude big O of n to the 5. Perhaps. All of them, however, do need to count, or they do need to be on an order of n. If any of them seem arbitrary for k in range 1 to 7 and doesn't relate to n, the input size, then we do not count that particular for loop. So in a for loop of 5 nested for loops, and maybe one of them is arbitrary in terms of how many times it goes around, we would still conclude that this algorithm is big O of n to the 4, provided that the other remaining 4 nested for loops count. We also have to pay attention to consecutive for loops, which we see in this example. We have the first green for loop for I in range n, followed by another for I in range n, and then an embedded for j in range I plus 1, n. Here we count the 2 nested for loops. In fact, if we have to create an equation, it would be big O of n plus n squared. Since we remove lower order terms and any constants associated, what's left is big O of n squared. So while we visually see 3 for loops here in this particular example, example number 2, 3 of them are not nested within each other. Therefore, this is big O of n squared, or a quadratic algorithm. As n doubles, in this case, the time actually quadruples. What about this? Well, we don't see any loops. We might say, well, is this constant time? In fact, in this case, we need to look at other elements of the code. I'll tell you ahead of time that this is a logarithmic algorithm. But how do I know this, other than the fact that I'm looking at this code and it's named binary search? But let's pretend it was called XYZ. How do you find visual cues in code to let you know that this might be a logarithmic algorithm? The key here is to find pieces of code that seem to calculate a middle point in the list, and then make a decision about one side or the other. When you reduce the input size by half with every iteration, this is a logarithmic relationship. This is effectively how algorithms like binary search work. You find the middle, you pick a side, then you operate on that one half only, and you ignore the other half of your data set. So half and half and half, again, this is a logarithmic relationship. So here, what are the visual cues? I see that I'm calculating a midpoint, I mid. Effectively, I'm taking my min and my max and dividing by 2. But also in this code, I'm making a determination of which side to concentrate on. A form of min changing to mid plus 1 and a form of max changing to mid minus 1. These are all giving me visual cues that I'm only looking at one half at a time at every iteration. Notice this is in a while loop. Therefore, this is a logarithmic algorithm.